Hey guys, welcome back to the Biomechanics 1 video series, looking at part 3 where we will be discussing angular acceleration. Okay, so by definition, angular acceleration is simply the time rate of change of angular velocity, right? So the time rate of change of angular velocity is equal to this angular acceleration. So mathematically, we introduce again a new symbol, the symbol alpha, which kind of looks like this squiggly fish, right? So this is alpha, and that is defined as this change in angular velocity over this change in time. So again, this change, or delta omega, is some final angular velocity minus some initial angular velocity. Again, this can be positive, negative, or zero, depending on the direction of rotation, which is really, really important. Remember that anti-clockwise is positive and clockwise is negative, and that this delta omega picks up the sign from the delta displacement, right? Delta theta. This change in time is always a positive quantity. In terms of the dimensional analysis of angular acceleration, what are the units that it is composed of? Well, it is composed of the units that are defined for angular velocity and the units of time. So from the earlier video, you guys would have realized that angular velocity is measured in radians per second, and time is always measured in seconds. So the SI unit for angular acceleration is radians per second squared. Notice again how this is similar to the linear acceleration formula, where we have linear acceleration being this change in velocity over some change in time, where again this was measured in meters per second squared, right? Again, very similar concepts and very similar ways of calculating it. Remember also that the angular acceleration is the slope of a angular velocity versus time graph. If the angular velocity versus time graph is constant, so when omega is constant, then that means that the angular acceleration is 0. When omega is positive and increasing, that means that angular acceleration will be some positive value, and when angular velocity is negative and decreasing, that means that angular acceleration is some negative value. So if I had some kind of angular velocity versus time graph, which looked something along these lines, where let's say, for example, at 1 second, it was 3 radians per second. At the 2-second mark, it was something like 6 radians per second. And at 3 seconds, it was something like 9 radians per second. Then what would be the angular acceleration? Well, again, it's the slope of this graph. So you guys should have a really good gist of what this will be for now, by now. So the slope is always the rise over run. You guys are going to be pros with this stuff by the end. Remember that this is the rise and this is the run. Okay? So the rise is this change in omega, which is change in angular velocity, and the run is this change in time, which is delta t. Let me just add this 3 in here quickly. So that's a 3. Okay, so if I had to take the slope, remember that this here will be my final angular velocity, and this here in this part of the analysis is my initial. So now I'm changing or analyzing this change in rise. So that is equal to my final, which is 9, minus my initial, which was 6, and my change in time is 3 seconds minus 1 second. So I'm sitting with 3 over 1, and that is in radians per second squared. I'll leave it as to you guys as an exercise to prove that the angular acceleration will be 3 radians per second squared all along this. So at 1 second, 2 seconds, or 3 seconds, it's just going to be a constant angular acceleration. So if I had to plot the acceleration versus time graph based on the values that I just calculated, at 1 second, 2 seconds, and 3 seconds, it's going to be this constant value of 3 radians per second squared. Remember that angular acceleration is measured in rads per second squared. Time is always in seconds. Earlier in the previous video, we discussed the fact that this is true, right? Angular acceleration is this change in angular velocity over change in time. If I wanted to be able to calculate the angular velocity, I could multiply this out. So I can say that angular velocity is equal to angular acceleration times some change in time, right? So if I was given an angular acceleration graph, I'll be able to calculate what the change in angular velocity is by looking at the area under the angular acceleration versus time graph. Okay, so let's just go about proving that for a second. So again, if I had this angular acceleration versus time graph, and I wanted to find out what the change in angular velocity was over the first second, I would look at the area under this graph, right? So remember that the area is base times height. And in this case, the base is 1 second, and the height is 3 radians per second squared, which gives me 3 radians per second. So you'll notice that radians per second is a angular velocity value. So it's saying that at 1 second, the angular velocity should have been 3 radians per second, and that's exactly what we have here. So at the 1 second mark, it was 3 radians per second. So that is saying that this change in angular velocity was this particular quantity. That's at 1 second. The change in angular velocity at 2 seconds, let's see what that should be. So that again would be the length of the base times the height, or the area under this particular graph. So again, this change in time is 2 seconds times this angular acceleration, which was 3, gives me 6 radians per second squared, and that's exactly what I had at the 2 second mark. Okay, and I'll leave it to you guys to do the third and final one, but you'll notice that it should be 9. If you've done everything correct, then that is what you'd get. So if I have an angular velocity versus time graph, I take the slope of that, I'll get the angular acceleration. If I have an angular acceleration versus time graph and I take the area underneath that graph, I'll be able to calculate the angular velocity, right? So graphical analysis can give me a whole host of insights into what is happening with a particular motion, with particular angular displacement, with particular angular velocities and particular angular accelerations, depending on the graphs that I have and how I interpret and analyze them. I'm going to give you guys a pretty tough one to assess and analyze here. All right. The fact of the matter is that I'm given this angular velocity versus time graph, where I start off with 6 radians per second and decrease ultimately to 0 at 3 and move to -2 radians per second at 4, and then it kind of stays there, parks off there, and keeps going at constant angular velocity throughout. So there's a couple of questions I need you guys to answer. A is find the change in displacement and angular displacement. Give your answer in radians as part 1, and part 2 in revolutions from t equals to 0 to t equals to 4 seconds. B asks you to find the angular accelerations at 3 seconds. C asks you to find the angular acceleration at 5 seconds. And finally, D is also subdivided into 2 parts. Find the average angular velocity and average angular acceleration from t equals to 0 to t equals to 4 seconds. All right, so try and work your way through that, and then we'll go through the answers. Okay, I'm assuming you guys have given it a go. So let's kind of see what we come up with. So part A, I'll just kind of do down here. So if I'm given an angular velocity versus time graph, and I'm asked to find the change in displacement, remember that this is where I have to find the area underneath the graph. So angular velocity is typically defined as the change in angular displacement over the change in time. But I can also find the change in angular displacement by multiplying this out. So if I have this angular velocity times time, the area underneath the graph of a angular velocity versus change in time graph will give me the change in angular displacement. Okay, so that in essence means that in the beginning here, if I find the area under this graph, this angular velocity versus time graph, just looking at this triangle for now, remember I have to do this from 0 to 4 seconds, so I'm just looking at this top part. It's a positive value. So the change in angular displacement is equal to the area under the graph. So the area of a triangle is equal to half the base times the height, which in this case, the base is 3. So I say half of 3 times, and the height is 6. Right, 3 times 6 is 18, and half of that is 9. So 9 radians. Okay, that's part 1. There's a second part to this, because I have to look from 0 to 4 seconds. This is just from 0 to 3 seconds. I'm sitting with another triangle here, which is given in negative numbers, right? So here, if I look at the area of this particular triangle, again, I'd have to look at the half of base times height, which is half of the base here is 1 times the height is -2, right, which would give me a value of -1 radians. So the total change in displacement, right, I'll just have a subset here, total is equal to 9 plus -1, giving me 8 radians. Okay, so this change in angular displacement in radians is 8. So that's part 1 taken care of. Part 2 is as follows. I'm asked to calculate it in revolutions. Remember that if I have a circle, right, if I'm going around the circle, one complete revolution is equal to 2 pi r, right? Or 2 pi radians. So therefore, I'm trying to find out, well, what is the equivalent in terms of revolutions if I've moved through 8 radians? So I'll divide both of these aspects by 2 pi to find out what 1 radian is in terms of revolutions. So if I divide this by 2 pi, I'll divide this by 2 pi. So it means that 1 radian is equal to 1 over 2 pi revolutions. Well, since I've got 8 radians, I'll multiply this side by 8, and therefore multiply this side by 8, and I have that 8 radians is equal to 8 over 2 pi revolutions, which simplifies to 4 over pi revolutions. Okay, so hopefully that makes sense and that wasn't too difficult to analyze. So part A is ticked off, done that. Okay, part 2 is find the acceleration, the angular acceleration at time is equal to 3 seconds. Well, if I've been given a angular velocity versus time graph, then I know the angular acceleration is equal to the slope of that particular graph. So I should be able to do that pretty comfortably. So if I was looking at the slope of this angular velocity versus time graph, the slope, remember, is equal to the change in angular velocity over the change in time. So I can just look at any points on this graph to be able to calculate that. I can just look at this first section here and do it pretty easily. So remember that this here is my final and this here is my initial. So I can say the final angular velocity is equal to 0. The initial is equal to 6 radians per second. The change in time is my final time, there's 3, and my initial was 0. So I'm sitting with negative 6 over 3, which is equal to negative 2. Remember, that's radians per second squared. All right, so at the 3-second mark, that is exactly what it is, because you can see it's true for 1 second, 2 seconds, 3 seconds, and even 4 seconds. So we can write that there is equal to negative 2 radians per second squared. Well, what is the angular acceleration at 5? So that's looking for the angular acceleration at this point in time over here. Come on. If I took the slope of this, what you would find is that, remember the slope where angular velocity is constant, that means the angular acceleration is 0. So I'll leave it as an exercise for you guys to prove that the acceleration during this point in time will be, the angular acceleration is equal to 0. So that should be my answer here, 0 radians per second squared. Okay, and then part D is again subdivided into 2 components. Find the average angular velocity. So remember, average angular velocity is just denoted with a bar, and average acceleration is just denoted with a bar. Between 0 to 4 seconds. So what is the average? You can see that the angular velocity tends to decrease all the time down to 4 over the 4 seconds, down from 6 to negative 2. So what is the average angular velocity? So let's just try and calculate it down here. Once I can figure out how this pen works. Okay, so in terms of part D, so section D, part 1, average angular velocity is equal to the change in the angular displacement over the change in time. But something that we did in section A already was to find out what this change in angular displacement was over those first 4 seconds. So we've already established that this change in angular displacement was, over those first 4 seconds, 8 radians. And the change in time, while it's over 4 seconds, gives me this. And therefore my average angular velocity from 0 to 4 seconds is equal to 2 radians per second. Nice. Okay, part 2 is what is the average angular acceleration? Well, the average angular acceleration over that period of time is looking at what is my change in angular velocity over my change in time. So over this 4-second period, my angular velocity over here at 4 seconds is equal to -2 radians, and my initial angular velocity was 6 radians. So if I had to plug that into my formula, this is -2 minus 6 radians per second over 4 minus 0, and I'm sitting with -8 over 4, and that gives me -2 radians per second squared. And you're done, right? So again, valuable information derived from just a simple, relatively simple graph. So there's lots of information that can kind of be gleaned from a angular velocity versus time graph. I can find both the acceleration in terms of defining the slope. I can also find the change in angular position by finding the area under the graph. Okay, it works both ways. So if I can do that quite comfortably, that will make life a lot easier. Again, there'll be a couple of examples for you guys to work through in the biomechanics manual. So again, if you guys get stuck on anything, please don't hesitate to ask. It's really important to rather get comfortable with all of this than just taking things for granted. I'll leave it there for now. In the next video, we'll look at the relationship between these angular and linear quantities with regards to one-dimensional motion. Okay, have a good one, guys. Thanks. Bye.